Hello, everybody. This is the second lecture on metal semiconductor contact. So we are now in part 3 of the course, semiconductor devices. Um, in the previous lecture, we have discussed the types of the metal semiconductor contact, ohmic and rectifying. We learned how to figure out if the contact is ohmic or rectifying, depending on whether the semiconductor is of p-type or n-type, and depending on the relation between the metal and semiconductors work functions. In this lecture, we will focus on the rectifying contacts. I will reiterate what I probably have said already. I do not remember really. So about the rectifying metal semiconductor contacts for N and P-type semiconductors, and then I will introduce an important technique which allows you to learn about the nature of the contact, ohmic or rectifying. It allows you to measure the concentration of the majority carriers, more precise, the doping level, in a rectifying, well, not necessarily rectifying, by measuring the capacitance voltage characteristics of a semiconductor metal contact. And it also allows you to measure what is called the built-in voltage. So let's consider the energy band diagram of a metal and an n-type semiconductor such that the semiconductor work function is smaller than the metal work function. This contact is ohmic because if you apply a positive bias to the metal relative to the semiconductor, you will be attracting the electrons from the semiconductor into the metal. Those electrons, the conduction electrons, they exist at the bottom of the conduction band. In order to make it into the metal, they need to overcome this energy barrier right here in the diagram. The energy barrier emerges due to the band bending, and when you apply a positive bias to the metal, you are reducing the height of this energy barrier. You are also reducing the size of the depletion region at the interface. So the current will be increasing. Actually, it will be increasing exponentially strongly with the applied bias, positive bias, direct bias. Whereas if you apply a negative bias to the metal relative to the semiconductor, your current, in principle, you are pushing the electrons from the metal into the semiconductor if you apply minus to the metal relative to the semiconductor. But those electrons cannot, they have two choices. They can either go into the valence band, like roll down this energy curve, like downhill, which would be great, or they should somehow get into the conduction band. Now they cannot go into the valence band from metal to semiconductor because all states, or practically all states in the valence band, are filled, so there are no empty states to go to. So the electrons must go into the conduction band of the semiconductor, but for that they need to overcome this energy barrier. It is called the Schottky barrier. The height of the Schottky barrier is practically independent of the applied voltage, and this Schottky barrier is pretty high. It is pretty big. So the current from the metal into the semiconductor will be quite low. Okay, and that's the rectifying effect. You have high exponentially increasing current if the bias is in forward direction, plus to the metal, minus to the semiconductor, and you will have the low saturation current if you apply bias in the reverse direction, that is minus to the metal and plus to the semiconductor. All right, so let's talk about these energy barriers. and the band bending, I will be discussing the ideal metal semiconductor contact, because the real life physics is a little bit more complicated. Well, much more complicated, really. So anyway, in the ideal metal semiconductor contact, you have band bending on the semiconductor side, and the size of that band bending is just the difference between the metal work function and the semiconductor work function. The reason is this: the Fermi levels of the semiconductor and the metal must align with each other, because the two systems come to thermal equilibrium with each other. Okay, the electrons get transferred between the two systems, metal and the semiconductor. Because the metal has a huge density of states at the Fermi energy, the metal acts as a heat bath from the point of view of the semiconductor. So the bands on the metal side practically do not bend, but it is the semiconductor bands that need to adjust themselves to ensure the alignment of the Fermi energies. And if the work function of the semiconductor, that is the energy difference between the Fermi energy and the vacuum energy, this is the work function. Actually, it is the other way around, to have it positive. Vacuum energy minus the Fermi energy. That's the work function. Anyway, like geometrically, it is obvious that if this is the metal work function, this is the semiconductor work function, Fermi energy must be the same. Hence, the size of the band bending is this difference, this energy difference, which is exactly the difference between the metal and the semiconductor work functions. Since the energy band diagram describes the electron energy, and electron energy is at the end of the day, electron energy is determined by the local value of the electric potential. Electron energy is the electron charge times the value of the electric potential. Electron charge is negative. So electric potential has the opposite side, opposite sign than the energy of the electron in the energy band diagram. This means that if the bands are bent up, then the value of the surface potential develops, and it is negative. Okay, so semiconductor surface is more negative than the semiconductor bulk. Now, by examining the energy band diagram, we can figure out the size of the Schottky barrier. That is, this barrier, this is the energy that an electron need to overcome in order to make it from the Fermi level on the metal side to the conduction band in the semiconductor, right? So geometrically, it is the metal work function, this energy difference, minus this energy difference, which is electron affinity of the semiconductor, the difference between the vacuum energy and the conduction band edge energy in the semiconductor. This is your Schottky barrier. I already said that we will be considering idealized metal semiconductor contacts, not the real life ones. In real life, this description is incomplete. So let me just tell you what happens in real life in words. I do not have slides for that, but I think it's a good thing, an honest thing to do, to tell you the truth. So in real life, we need to introduce a third player in this game. So we have two players, metal and the semiconductor, but in real life, we have a third player. It is the surface states. Now, surface states are defects, impurities on the surface of the semiconductor, dangling bonds. Now, what are dangling bonds? The bonds that dangle. So let's say it is silicon, and you cut silicon, and when you cut silicon, you cut the bonds which in the cutting plane you cut the bonds which connect two neighboring silicon atoms. So those bonds which along which or across which you cut become unsaturated. You terminate the crystal at the surface, and some of the bonds of the surface atoms become unsaturated. Those bonds are called the dangling bonds. And those dangling bonds can trap electrons. That is, they introduce additional energy levels. So those energy levels are called surface states. They exist inside the band gap of the semiconductor. To minimize the energy, the surface of the semiconductor, if you just cut the surface of a semiconductor and no metal is attached, typically the semiconductor surface undergoes the process called surface reconstruction. It is the fact if you cut the silicon along the 100 plane, then the surface that you will see the atoms on the surface will be arranged not as they are arranged in the 100 plane in the semiconductor bulk. They will change their mutual arrangement just to saturate the dangling bonds. This is called the surface reconstruction. So typically they may form like grooves of atoms consisting of like a row of two atoms or something like that. All right. So now, if you consider the presence, if you introduce the surface states into the model, into the picture, then the semiconductor is not connected to the metal directly. The semiconductor bulk is connected, it communicates with the surface states, and the surface states communicate with the metal. The energies of those surface states lie inside the band gap, and you can form some sort of an average energy. More precisely, it is called the charge neutrality level. It is the probability of occupation of those surface states is still given by the Fermi-Dirac distribution. And the Fermi energy which enters that Fermi-Dirac distribution must be such that the charge neutrality condition for the surface is fulfilled. So that value of the Fermi energy is called the charge neutrality level. And now when you create a contact between the semiconductor and your metal, then the charge neutrality level of the semiconductor becomes aligned with the Fermi energy of the metal. Now the surface states act from the point of view of the semiconductor bulk. The surface states act as a heat bath, and now the semiconductor bulk must align its own Fermi energy with this charge neutrality level, and it is this process, this phenomenon is called the pinning of Fermi energy to the surface states. Right? So the size of the band bending becomes determined not just by the difference in the semiconductor and the metal work functions, but by the surface states due to this Fermi level pinning effect. And in fact, it turns out that the value of the Schottky barrier, which is written as the difference between the metal work function and the semiconductor electron affinity, it turns out to be almost independent on the metal work function. It is mostly determined in real life. It is mostly determined by the charge neutrality level. So this is what happens in real life. This is the physics of real metal semiconductor contacts. Okay, I have told you these words as to my best ability. But now let us return to this to our ideal world and try and analyze, understand the ideal metal semiconductor contact, which is my primary goal in this course. Now, okay, let us return to the metal p-type semiconductor rectifying contact, in which ideal contact. So in this case, the semiconductor work function is higher than the metal's work function, and the contact is rectifying for the following reason. Now, if you apply the negative bias to the metal, you are attracting the majority holes from the semiconductor into the metal, the majority holes. Or you can think of it differently. If you are applying a negative bias to the metal, you are pushing the electrons from the metal into the semiconductor. Those electrons happily fall into the valence band of the semiconductor. Since this is a p-type semiconductor, the valence band has a lot of empty states, the holes. So the electrons now from the metal can get into the valence band, and they continue moving away from the interface. Or like another picture would be you are retracting holes from the semiconductor, you are pushing the electrons from metal into the semiconductor, the electron and hole armies meet at the interface and mutually recombine. On the other hand, if you apply a positive voltage to the metal relative to the semiconductor, then you are pushing away the majority holes on the metal side, on the semiconductor side. You are pushing them away from the metal. You're pulling away the electrons on the metal side. You are pulling away the electrons from the interface, and so all you are doing is increasing the size of this depletion region with very little current flowing. Now, of course, some electrons, for positive bias applied to the metal, some electrons from the valence band will enter the metal. They will be attracted by that positive bias. But in order to enter the metal, they need to overcome the Schottky barrier right here. The size of that Schottky barrier is high, so it is difficult for them to overcome that high barrier, but still some of them will be able to do that. So some current, the saturation current, will be flowing for a positive bias, positive voltage applied to the metal. So you have exponentially increasing current when the voltage applied to the metal is negative, and very small but non-zero current when the voltage applied to the metal is positive. The built-in voltage, we follow the convention in which the built-in voltage is always positive. So it is the difference between the semiconductor and the metal work functions, because the semiconductor work function is bigger than the metal work function. Since the semiconductor bands are bent down and the energy which you plot on the energy band diagram are the energies of an electron. So this implies that the surface potential of on the surface is positive, right? So the surface is more positive than the bulk. And the size of the Schottky barrier for this ideal junction, which is our primary interest. Okay, we can figure it out by considering this energy band diagram here. So E chi plus the band gap energy is the energy difference between the vacuum energy on the semiconductor side and the valence band energy at the top of the valence band. So this is E chi plus E gap. Now, if you subtract from this energy difference, if you subtract the metal work function, what will you get? So this is E chi on the interface. It's better to look at the interface rather than the bulk. This is E chi. This is E gap. So E chi plus E gap is the energy difference between here and here. Subtract the metal work function between here and here, and this is what you get, the Schottky barrier. All right? So these energy relations can be established by looking at the energy band diagram, examining the energy band diagram. Oops. Now I would like to describe a powerful technique to learn something about the semiconductor, in particular, to measure experimentally the built-in voltage. The built-in voltage and the doping level by performing the capacitance voltage measurement. So if you have a rectifying metal semiconductor contact, this means that there is a depletion region, and that depletion region can be approximated as a layer of insulator. It is an insulating layer. Now, in practice, in reality, the concentration of charge carriers can never drop to zero in the depletion region. The lowest value, the lowest concentration of charge carriers of either type is the intrinsic concentration. Yeah. But if the Fermi energy is close to but the intrinsic concentration is much smaller than the doping level. So you can model the depletion region as a capacitor. It is a leaky capacitor, but it is a capacitor, and you can measure the capacitance. When you apply a voltage, the value of the surface potential changes from the built-in voltage value, we built in, to the difference between the applied voltage and the value of the built-in voltage. So for N-type semiconductor, the value of the surface potential is negative. At zero applied bias, it is negative built-in voltage at zero applied bias for N-type semiconductor. But if you apply a voltage, then the value of the surface potential becomes the external voltage that you apply to the metal minus the built-in voltage. And the depletion region width has been derived. Recall our lectures. I forgot the lecture number, but we have discussed the solution of the Poisson-Boltzmann equation with the help of the depletion approximation. So within that approximation, we have derived this formula for the depletion region width. Square root of twice the dielectric constant of the material, epsilon naught epsilon, times the value of the surface potential divided by the elementary charge and the concentration of the donors. Even if your semiconductor metal contact is ohmic, you still can, that is, even if the semiconductor work function is larger than the metal work function and the semiconductor is of N-type, you still can produce a depletion region if your voltage applied to the metal is sufficiently large in magnitude, and you would need to have to apply a negative bias. Like in order to produce a depletion region, you want to push away the majority electrons away from the interface in the semiconductor. So if you increase the magnitude of your negative bias to the metal, you will eventually produce a depletion region. The width of that depletion region will be given by the same formula. Now, we are modeling the depletion region as a as an insulating layer, and if you have an insulating layer, then it has the capacitance. The capacitance of a dielectric parallel plate capacitor filled with a dielectric whose dielectric constant is epsilon is epsilon naught epsilon times the area of the capacitor divided by the distance between the capacitor plates. And the distance between the capacitor plates is just the depletion region, W. In order to make this result independent on the geometry, let us divide by the surface area and introduce capacitance per unit area, which would be just the dielectric constant, epsilon naught epsilon, divided by the depletion region width W, and plug in this formula for the depletion region width, and this is what you get. Now, if you measure the inverse capacitance squared, take 1 over C prime, and square the result, then you will obtain something which is proportional to the applied voltage. It is a decreasing, linearly decreasing function of the voltage. So if you measure, you can measure the depletion region capacitance using a simple farad meter. You can do this measurement for different measurements for different values of the applied bias, and then you will get a linear graph for the inverse capacitance squared versus voltage. Now, you can extrapolate this linear curve to the value when the inverse capacitance squared becomes 0. And this value, this extrapolated voltage value, is the built-in voltage. The slope of this straight line, 1 over C prime squared versus V, is the whatever multiplies the difference between the built-in voltage and the applied voltage V. So it is 2 divided by elementary charge epsilon naught epsilon times the donor concentration for n-type semiconductors. And of course, a similar expression holds if your semiconductor is of p-type. With 2 differences. One difference is obvious. You need to replace the donor concentration with acceptor concentration. And second, the difference between the built-in voltage and the applied voltage changes sign. So in the brackets, it will be V minus V built in. So these are the characteristic shapes, the patterns, the inverse capacitance squared versus applied voltage curves for P and N semiconductor contacts with the metal for the cases when the contact is ohmic and rectifying. So we can understand these curves by thinking what happens to the majority carriers when you apply positive or negative bias depending on the type of the semiconductor. So for example, if the semiconductor is of N-type, then you need to, the capacitance of the depletion region exists only if you have the depletion region. And the depletion region increases in width as you increase the magnitude of your negative bias applied to the metal. Okay. So if the voltage applied to the metal is large and negative, the depletion region becomes large. It increases with the voltage and if it is negative. If the contact is rectifying, then this means that the depletion region exists also when there is no bias applied to the metal. That is, when the semiconductor and metal are kept under the same potential. If the depletion region exists when the voltage on the metal side is 0, then also the capacitance, it has the capacitance. So the capacitance, inverse capacitance squared versus voltage curves crosses the vertical, the y-axis at 0 applied voltage. Now, on the other hand, if the contact is ohmic, then and your voltage applied to the metal is positive, then there is no depletion region. So there is nothing. The value of inverse capacitance squared is 0. You decrease the voltage in the negative direction, and at some point, when the voltage applied to the metal is negative and has some finite value, you create the depletion region, because you have caused at this voltage value, the bending size is 0, and then as you keep decreasing the voltage below this negative value, the semiconductor bands start bending in the opposite direction than at 0 voltage, and so the depletion region starts growing, and it grows for the large negative as you increase the magnitude of negative voltage applied to the metal. Now, if your semiconductor is of p-type and the contact is rectifying, then there are two things that can be said about the inverse capacitance squared versus voltage plot. The first thing is that the depletion region for rectifying contact, the depletion region exists also for 0 applied voltage, and the depletion region increases in size as you increase the voltage in the positive direction. Voltage V is the voltage applied to the metal, whereas the semiconductor is assumed to be grounded. Okay. So as the depletion region grows in size, the capacitance due to this depletion region, which is inversely proportional to the depletion region size, the capacitance decreases, so the inverse capacitance squared increases with the voltage. If you decrease the voltage starting from 0 value, so now you go in the negative bias toward you're increasing the negative bias, then eventually you will destroy the depletion region. The bending becomes 0 at this point. And then if you keep decreasing the bias, there is no depletion region in the semiconductor. Now for ohmic contact between a metal and a p-type semiconductor, no depletion region at 0 voltage on the metal. You increase the voltage on the metal side, so it is positive. At some non-zero voltage value, you produce the depletion region, and then the depletion region increases in size, meaning that the capacitance of the depletion region decreases, meaning that the inverse capacitance squared increases. And the final point that I would like to make about all these 4 graphs is this saturation value. So eventually, as you are increasing the depletion region by either increasing or decreasing the voltage, depending on the N-type or P-type semiconductor, you cannot, so better to say, if you're increasing the size of the depletion region by increasing the magnitude of the voltage on the metal, you cannot increase the size of the depletion region indefinitely, because eventually you will reach the voltage at which the inversion layer in the semiconductor, at the semiconductor surface, starts to form. Recall our last lecture on the topic of the solution of the Poisson-Boltzmann equation. And when the inversion layer starts forming, further increase of the voltage magnitude results in an increase of the concentration of minority carriers in the inversion layer. But the depletion region does not grow anymore, which means that the capacitance saturates at some value. So this is the saturation of the capacitance versus voltage curves. All right, so that's all that I wanted to tell you in this lecture. Thank you all for your kind attention, and we have 1 lecture left about the metal semiconductor contacts. We will need to discuss the current voltage curve. Goodbye.